A wonderful day to everyone. Good morning and welcome to our general chemistry class. Before we start, I just want to ask everyone to get ready for the presentations. Today we are doing the reporting for limiting reagents, mainly the topics explaining the concept of limiting reagent in a chemical reaction and identifying the excess reagent and calculating percent yield and theoretical yield of the reaction. But first, let me discuss the meaning of limiting reagents. The limiting reactant or limiting reagent is the reactant that gets consumed first in a chemical reaction and therefore limits how much product can be formed. We will encounter what this means as we go on with the reporting. Better be ready and listen carefully in the presentation for better understanding of the topics. For now, let's welcome the first group who will discuss the first topic under limiting reagents. The first topic is about explaining the concept of limiting reagent in a chemical reaction and identifying the excess reagents. Please listen carefully as this will help everyone for the next topic.
Today, we will be presenting our topic by explaining how to limit reagents in a chemical reaction and how to identify the excess reagents. Before we move on to our group presentation, let us all welcome our presenters. Yours truly, Samantha Gapido, Ms. Dizaila May Areve, and Ms. Erich Ann Ferreras. Our objectives for this presentation is to first introduce what limiting and excess reagents are, present the steps, and provide examples. Let's first start to why the reactions stop. When there is not enough of one reactant in a chemical reaction, the reaction stops abruptly. In nature, a reaction that is carried out in a laboratory, usually one or more of the reactants are in excess while one is limited. The amount of product depends on the reactant that is limited. The following scenarios illustrate the significance of limiting reagents. Here, in the first scenario, there are 5 hot dogs and 4 buns. After it combines, 4 hot dogs in a bun are formed and there is one leftover hot dog. Here, on the next scenario, there are 8 hydrogen elements and 3 oxygen elements that yields and form 3 water elements or H2O, wherein there are 2 hydrogen elements left. Given in the first scenario, after 4 hot dog sandwiches are formed, we are not able to make more since there were no more buns available to create a hot dog sandwich. Thus, the bun was a limiting reagent. For a more understandable explanation, the limiting reactant or limiting reagent is the first reactant consumed in a chemical reaction, wherein it limits the amount of product that can be produced. A portion of all the other reactants remains after the reaction stops. Reactants left over when a reaction stops are excess reagent. The left hot dog on scenario 1 was a excess reagent. The excess reactant is the reactant in a chemical reaction with a greater amount than necessary to react completely with the limiting reactant. It is the reactant that remains after a chemical reaction has reached equilibrium.
For us to determine the limiting and excess reagents, we've utilized two methods. Shown in the screen is the first method that we used, which is to find the limiting reagent by looking at the number of moles of each reactant. The first step in this method was to determine the balanced chemical equation for the chemical reaction. Then second is to convert all given information into moles, or most likely through the use of molar mass as a conversion factor. For the third step, we then calculate the mole ratio from the given information, compare the calculated ratio to the actual ratio, and then for the fourth, use the amount of limiting reactant to calculate the amount of product produced. And lastly, if necessary, calculate how much is left in excess of the non-limiting reagent. Moving on to the second method that we've used in determining the limiting and excess reagents is to find the limiting reagent by calculating and comparing the amount of product each reactant will produce. In this second method, the first step was to balance the chemical equation for the chemical reaction. And then second, convert the given information into moles. For the third step is to use stoichiometry for each individual reactant to find the mass of product produced. In the fourth and fifth step, we then identified which is the limiting reagent and the excess reagent. The limiting reagent is the reactant that produces a lesser amount of product, where in the other hand, the excess reagent is the reactant that produces a larger amount of product. The last step in this method was to find the amount of remaining excess reactant, subtract the mass of excess reagent consumed from the total mass of excess reagent given. And that was the two methods that we've employed in determining the limiting and excess reagent.
In the first example, we will use the first method. The chemical reaction stated in the first example is glucose reacts to 6 oxygen gas to produce 6 carbon dioxide, water, and energy. Since the balanced chemical equation is given, we will now move on to the second step, in which we will convert the equation into moles. In doing this, we will multiply 25 grams with 180.6 grams of every 1 mole and 40 grams with 32 grams of every 1 mole. To get the mole ratio of glucose, we will multiply the moles 1.25 moles of oxygen gas with 6 moles of oxygen gas for every 1 mole found in glucose. On the other hand, to get the amount of oxygen gas produced, we will multiply the limiting reactant, which is 0.1388 moles of glucose, with 1 mole glucose for every 6 mole of oxygen gas. To get the carbon dioxide produced, we will multiply the moles of glucose with 6, which results to 0.8328 moles. And the last step is to get the difference between the moles of oxygen gas and carbon dioxide produced to get the excess reagent. Thus, 0.4172 is the moles of oxygen gas left over. For the second example, the chemical reaction given is propane reacts to oxygen gas to produce carbon dioxide and water. We will add 3 in the carbon dioxide and 4 in the water to make it balanced. After that, we will convert it into moles. To get the moles of oxygen gas, we will multiply 2 moles of propane with 1 mole of propane for every mole found in oxygen gas. On the other hand, to get the mole of propane, we will multiply 8 moles of oxygen gas with 5 moles of oxygen gas for every 3 moles found in propane. The reactant that produces a smaller amount of the product is the limiting reactant. Thus, oxygen gas is the limiting reagent. Meanwhile, the reactant that produces the larger amount is the excess reagent, which is the propane. To get the leftover reagent, we will multiply 8 moles of oxygen gas with 5 moles of oxygen gas for every mole found in propane. We will minus the total moles with the react moles. Thus, the leftover reagent is 0.4 mole. For the last example, we use the second method. Here, we have a chemical reaction. Magnesium reacts to oxygen gas to produce magnesium oxide. We can see that it is not balanced yet, so we will add 2 in the magnesium and 2 in the magnesium oxide so that it will become balanced. After that, we will convert mass to moles and stoichiometry. We first convert the 2.40 grams of magnesium into grams of magnesium oxide. We will multiply 10 grams of magnesium to the value of mole of magnesium to grams, which is 1 mole of magnesium over 24.31 grams of magnesium. Next, we will multiply it to the times that the magnesium oxide will appear over the times that the magnesium will appear. This will be the 2 mole of magnesium oxide over 2 mole of magnesium. After this, we will multiply it to the value of 1 mole of magnesium oxide, which is the equation 40.31 grams of magnesium oxide over 1 mole of magnesium oxide. This whole solution will result to 3.98 grams of magnesium oxide. The next one is converting 10 grams of oxygen gas to grams of magnesium oxide. The same with the process of converting the mass of magnesium to mass of magnesium oxide. We multiply the mass of oxygen gas to the value of 1 mole of oxygen gas to its mass, which is the equation 1 mole of oxygen gas over 32 grams of oxygen gas, then multiply it to the times that the magnesium appeared over the times that the magnesium gas appeared, as seen in the solution. It is the equation 2 moles of magnesium oxide over 1 mole of oxygen gas. After this, we will multiply it to the value of 1 mole of magnesium oxide to mass, which is 40.13 grams. Thus, the result will be 25.2 grams of magnesium oxide. The reactant that produces a smaller amount of product is the limiting reactant. Thus, magnesium is the limiting reagent. Meanwhile, the reactant that produces the larger amount is the excess reagent, which is the oxygen gas. The last step is finding the amount of remaining excess reactant by subtracting the mass of the excess reagent consumed from the total mass of excess reagent given. We can either use the mass of excess reagent calculated using the limiting reagent or the one calculated using the mass of the product. Either way will result to 1.58 grams of oxygen gas that will be used in getting the mass in excess. With the solution mass of total excess reagent given minus mass of excess reagent consumed in the reaction, we will get 8.42 grams of oxygen, which is the excess. That's it for our presentation. I hope you gathered new knowledge and information about limiting and excess reagents.
Thank you for the first presenters and thank you for that knowledgeable presentation. The next reporting is about calculating percent yield and theoretical yield of the reaction.
Good morning. In this report, we're going to discuss calculating percent yield and theoretical yield of the reaction. But let me first introduce the presenters. Yours truly, Alessandra Balde, Chininina Bergo, and Maria Janine Gubaya.
What is percent yield? To measure how successful a reaction has been, chemists need a measurement which is called the percentage yield. The percentage yield is the ratio of the actual yield to the theoretical yield multiplied by 100. How do we get or calculate the percentage yield? For calculating the percentage yield of a chemical reaction, it is primarily necessary to determine how much of the product should be formed based on the stoichiometric calculations. These are the 4 steps in calculating percent yield. First step, determine the theoretical yield. Theoretical yield is important because it indicates the potential results or product of a reaction at maximum performance. Second step, record actual yield. When calculated, the actual yield reveals the true amount of product produced by the reaction. Third step, divide actual yield by theoretical yield. Dividing the actual by theoretical yield provides the decimal percentage of the percent yield. Fourth step, multiply by 100 to convert to a percentage. To find the percent yield and calculate a full percentage, take the decimal results from the above step and multiply it by 100. This is the percent yield of a chemical reaction and helps to make the most product with the least waste while serving to indicate the efficiency of a method.
If there is percent yield, there is also theoretical yield. What is theoretical yield? Theoretical yield is the number of potential products created when chemical react. This is assuming that all products were used to their complete capacity and the reaction did not finish early. The basis of this idea is first a balanced equation. Once the equation is balanced, calculate for the theoretical yield. Step 1. Depending on your chemical, whether it is solid, liquid, or gas, you will determine the number of mole for each reactant being used. For solids, the mass of a chemical reactant is divided by its molecular weight. Step 2. Determine limiting reagent. Identify the chemical reactant with the smallest mole number by multiplying the molecular mass by the number of mole in each equation. The answer, which produces the smallest number, is the limiting reagent. It is the reactant that you will run out of fastest thus limiting your results or product. Step 3. Determine the ratio. Using the chemical equation, multiply the ratio between the limiting reagent and the product by limiting the reagent's number of moles. Step 4. Multiply again. The last step to determine the theoretical yield is to multiply the product's number of mole by the product's molecular weight.
After the discussion of the meaning and steps of percent and theoretical yield, we now proceed with the examples. In the first example, upon reaction of 1.274 grams of copper sulfate with excess zinc metal, 0.392 grams of copper metal was obtained according to the equation. Copper sulfate reacts to zinc to produce copper and zinc sulfate. We first identify the given, which are 1.274 grams of copper sulfate and 0.392 grams of copper metal, which is the actual yield. Then we see that the missing value is the percent yield. We then solve it using a step-by-step procedure. First, we list other known quantities, which are 1 mole of copper sulfate, which is equal to 159.62 grams per mole, and 1 mole of copper metal, which is equal to 63.55 grams per mole. And since the amount of product in grams is not required, only the molar mass of the reactants is needed. Next, we see if the equation is balanced. Since the equation is already balanced, we move on to the next step. For better understanding, we prepared a concept map as shown in the presentation and used the proper conversion factor. The provided information identifies copper sulfate as the limiting reactant, and so the theoretical yield is found by performing mass-to-mass calculation based on the initial amount of copper sulfate. The next step is to cancel units and calculate. We multiply 1.274 grams of copper sulfate to the value of 1 mole of copper sulfate to grams, which is the equation of 1 mole of copper sulfate over 159.52 grams of copper sulfate. Then multiply it to 1 mole of copper over 1 mole of copper sulfate, since that is the number of times that copper and copper sulfate appeared in the equation. And then lastly, we multiply it to the value of 1 mole of copper to grams, which is then seen in the equation as 63.55 grams of copper over 1 mole of copper. As we go on with the equation, we also cancel those units that are the same. After that, we see that the whole situation resulted in 0.5072, which is then the theoretical yield. The last step is to now find the percent yield. Using the equation, percent yield is equal to actual yield with a value of 0.392 grams over the theoretical yield with a value of 0.5072 grams multiplied by 100%. This results to 77.3%, and since the actual yield is slightly less than the theoretical yield, the percent yield is just under 100%. The second example, potassium chlorate, decomposes upon slight heating in the presence of a catalyst. According to the reaction below, 2 potassium chlorate was produced by 2 potassium chloride that reacts with 3 oxygen gas. In a certain experiment, 40 grams of potassium chlorate is heated until it completely decomposes. The experiment is performed and the oxygen gas is collected, and its mass is found to be 14.9 grams. We must find the theoretical yield of oxygen gas and the percent yield of the reaction. First is to write down the given, which are mass of potassium chlorate 40 grams and mass of oxygen gas collected 14.9 grams. Then the other known quantities, which are 1 mole of potassium chlorate, which is 122.55 grams per mole, and 1 mole of oxygen gas, which is 32 grams per mole. We now apply stoichiometry to convert from the mass of a reactant to the mass of a product. Using the illustration above, we can now see the converted values. Then we solve for the theoretical yield using the equation. We multiply 40 grams of potassium chlorate to the value of 1 mole of potassium chlorate to grams, which is the equation 1 mole of potassium chlorate over 122.55 grams of potassium chlorate. Then multiply it to the number of oxygen gas that appeared over the number of potassium chlorate that appeared in the reaction. We can see it as 3 moles of oxygen gas over 2 moles of potassium chloride. Lastly, we multiply it to the value of 1 mole of oxygen gas to grams, which is the equation 32 grams of oxygen gas over 1 mole of oxygen gas. It resulted in 15.7 grams of oxygen gas, which is now the value of the theoretical yield. Lastly, we calculate the percent yield. Using the given theoretical yield is equal to 15.67 grams, we must use the unrounded number for the calculation and actual yield 14.9 grams. To calculate the percent yield, we just need to substitute the values we get to the equation percent yield equals actual yield over theoretical yield times 100%. The percent yield equation will be like percent yield equals 14.9 grams over 15.67 grams times 100%, which resulted to 94.9%. We can say that the percent yield is just under 100%. In summarization, we can see that theoretical yield is calculated based on the stoichiometry of the chemical equation. Actual yield is experimentally determined. Percent yield is determined by calculating the ratio of actual yield to theoretical yield. That's all. Thank you.
That was a wonderful reporting, everyone. Thank you so much for that reporting and thank you for listening. I hope you understand our topic today. Have a good day, and if there's no question, this is the end of our reporting.